Three different sources of sound give voice to musical instruments. Vibrating columns of air, as in the woodwinds, surfaces such as drum heads and cymbals, and vibrating strings, such as those of the string section. But whether or not a sound is musical, each of the countless sounds in our environment originates in some object that vibrates. In this film, we shall study how sounds are produced and the principal auditory differences of sound. To begin with, what is involved in producing sound? To help answer this question, we experiment first with a tuning fork. When the fork is struck, its prongs begin to vibrate. These vibrations set up invisible waves in the surrounding air. We can picture these waves as animated drawings. Striking the prongs distorts them. Like other solid objects, these prongs resist distortion. They spring back and forth, thus producing new distortions. Each movement or vibration sets up new disturbances, or sound wave impulses. These continue as long as the prongs are in motion. The speed with which sound waves move depends upon the medium through which they pass. We will assume that these waves are being transmitted by air molecules. Every time the prongs move apart, they push against the adjacent air. In turn, this movement affects the air further on. In this segment of the wave, we can see that some molecules are pushed relatively close together. These represent condensations of air. Each time the prongs spring inward, a partial vacuum forms in their vicinity. Air molecules nearby move into this vacuum, leaving a rarefied zone behind. Thus, there are alternate zones of condensation and rarefaction of the air. The number of times a given molecule moves back and forth in 1 second is the frequency of the wave. In one complete vibration, indicated here by the bracket, sound travels a distance of 1 wavelength. The velocity of any sound wave equals its wavelength times its frequency. We can record pressure variations in sound waves with this kind of instrument, an oscillograph. Sound waves are striking the diaphragm at the left. The stylus records the sound waves as a graph. Later, we shall use such graphs to represent sound waves. Condensations cause the stylus to move upward. Rarefactions cause it to move downward. So far, we've seen how sound waves are produced. Next, we'll identify 3 auditory effects of musical sounds: loudness, pitch, and quality. We begin with loudness. Every sound sets up a disturbance in the transmitting medium. The larger the disturbance or displacement of the individual particles, the greater is the height of its graph above the neutral line. This displacement above the neutral line is called amplitude, and it is amplitude that determines loudness. As the amplitude of a sound increases, its loudness increases. Next, let us consider pitch, the auditory effect of frequency. First, we hear the sound of middle C. Next, we hear G below middle C. And now the sound of C below middle C. What causes such differences in pitch? To explain such differences, we picture 2 different sound waves. Here, the lower fork makes more complete vibrations per second. Therefore, its frequency is greater. It is evident that the one with the greater frequency has the higher pitch. The frequency of a vibrating string depends upon the material it's made of and its density, tension, and length. Different instruments produce sounds of different tonal quality, even when playing the same basic frequencies. Each vibrating string may be made to produce different tones. To explain some of the reasons for this, let us observe this string. Here there is no motion at these endpoints or nodes. The string vibrates along its full length and produces its longest possible wavelength. This is the lowest or fundamental frequency of the string, sometimes called the first partial. If the string vibrates in two segments, it produces a wavelength that's 1/2 that of the fundamental. This is the first overtone, which may be called the second partial. Since wavelength is inversely proportional to frequency, the frequency of the first overtone is twice that of the fundamental. When the string vibrates in 3 segments, it produces its second overtone, the third partial. Here, the frequency is 3 times that of the fundamental. But usually, several different modes of vibration occur simultaneously. The result is a compound waveform. Here we represent the fundamental tone supplemented by its first and second overtones. Differences in the audible components of a sound determine its quality. Quality helps us recognize the characteristic sounds of various musical instruments and distinguish one voice from another. With this oscilloscope, we can represent as waves the sounds being produced and see their different modes of vibration, as in the case of vibrating strings. Besides strings, you've already considered vibrating surfaces. Vibrations from such diaphragms are often quite complex. This diaphragm, for example, vibrates in a number of different segments. The third of the principal sources of sound is the vibrating column of air. The organ pipe, like the woodwind, produces sound by means of such an air column. Often the exposed pipes of an organ are merely decorative, and sounds are produced by the pipes in the organ loft. The wavelengths fitting the shorter pipes are shorter, and their frequencies are greater than the longer pipes. Consequently, the shorter pipes produce the sounds of higher pitch. The different kinds of pipes produce different qualities of sound. The organist uses stops and keys and pedals to admit compressed air into the pipes. Besides woodwind instruments and organ pipes, another mechanism that depends upon a vibrating column of air for its sound is the vocal mechanism of man. Here, sound waves result from vibrations of air that start in the vocal folds of the trachea. These waves are reflected back and forth in the cavities of the mouth, nose, and head, thus producing the complex sounds of speech and song. So we've sampled a few out of the multitude of sounds in our environment and have studied the meanings of loudness, pitch, and quality. From the vast number of vibrations that we interpret as sounds, we may gather a wealth of meaning and enjoyment.